Right. I think we'll give people like a minute to join, and then we'll start the conference. Very fun to see so many people joining. All right, I think we'll get started. Hello, everyone, and welcome back to the Understanding Latency webinar series. My name is Bjørn Teigen Monclair. I am VP of Network Intelligence at CUJO AI, and I will be your host today. Before we begin, I want to acknowledge the CUJO marketing team who has made this event happen behind the scenes, especially Victoria Wilke, who has sent many emails and coordinated all the speakers. They've created the swag, kept the website up to date, make sure people know about the event. I think they've done an amazing job, as the participant number here shows. So thank you very much for doing that. And then before we jump in, I want to take a moment to acknowledge someone who has had an outsized impact on this entire topic, Dave Tott. Dave was a pioneer in the fight against buffer bloat and a driving force behind the low latency community. He passed away back in April this year, and many of us learned from his writing, his code, his uncompromising focus on real user experience, and his generosity and time with his time and his insights. So we're very grateful for what he built and for the community that he helped shape. And later today, Frantisek Borsik, friend and colleague of Dave, will present about LibreQoS, which is one of the many things that Dave built in his life. And then I also want to sincerely thank all of our speakers for taking the time to share their expertise with the community. We're thrilled to have such an excellent group of speakers contributing to this event, and we really appreciate the effort that goes into preparing these talks. We have a very diverse group of speakers this year in terms of perspectives and experience. We have folks from academia, startups, bigger startups, giant corporations, superscalers, industry analysts, standards bodies, and more. So if you care about network performance, there should be something for you here for sure. Today is a relatively fast-paced program, short talks, lots of ideas, and hopefully there will also be time for questions after each speaker. I'll go through some of the practical details. So this is a knowledge-sharing event focused on practical latency, how to measure it, understand it, and improve it. The full agenda is available on the website. So let me just quickly share my screen here. I think you can now see the website. So understandinglatency.com. I just want to show you this because this is where you will be able to find all of the sessions after the event is finished. So here we have the agenda for this year's event with all of the speakers listed with the titles of their talks. And then if you scroll a bit further down, we have the agenda from last year's event. And if you see here, we have these watch session links, and we will do the same thing this year, putting the entire event on YouTube and then linking to each of the talks here. So it should be easy to find if there's a session you want to see again, or if you want to share it with someone. All right. And then please use the Q&A feature for your questions. There is a Q&A button at the bottom of your screen, which allows you to submit a question that is then visible to all of the speakers. And if there is time whenever a speaker is finished talking for Q&A, we will try to fit in some questions and answer them live. And then if there isn't time to answer questions live, I hope that the speakers will take a few minutes to answer the questions in the chat. And then finally, I think I already mentioned this, but we are recording today's session, which includes the Q&A. So if you do ask a question, please bear in mind that that will also be part of the published recordings. So with that, let's get started. Our first speaker today is Gavin Young, Vodafone's head of Fixed Access Center of Excellence. And within Vodafone Group, Gavin is responsible for fixed broadband access technology strategy, architecture, vendor roadmaps, and standards across the countries where Vodafone has fixed access assets, spanning fiber, cable, and DSL, plus fixed mobile convergence, virtualization, and network performance optimization. So Gavin has a lot of things on his plate. And Gavin, over to you.
Thank you, Bjørn. Let me share my screen here. Okay, hopefully everyone can see that. Thank you so much to CUJO AI for inviting us to this great series of events. For anyone passionate about latency and network performance, I think this is the place to be. You'd really find these events very useful and insightful. So what I'd like to talk to you today is about some of the work we've been doing in different areas relating to latency. But let's start with what we're trying to achieve. So our overall vision is that we want customers to not notice that there's a network delivering their applications. They don't know there's a network between their device and the content or application provider. And in order to achieve that, speed is not enough. We want to make the network invisible. And really where we want to get to is a much more tactile broadband internet experience. And that means we need to measure and mitigate latency. And today we're going to focus a bit more on the measurement aspects. So we're shifting, as I think you'll probably hear from a few speakers, we're shifting from the kind of speed, the bandwidth era to the experience era. And that means instead of, good things about network being big in quantity like bandwidth and speed and logical extension being infinite bandwidth, we're trying to minimize the bad things, which is, defects like packet loss and latency. And hence enhance the quality. It's easier to measure how close you are to zero than how close you are to infinity, and that's the focus of some of our measurements. But if we look specifically at some of the questions we're trying to answer with what we're doing, it's questions like, why is my broadband laggy? Where is the problem? Is it in my Wi-Fi network? Is it in the ISP, the network operator's network, or is it in the wider internet? And is it just this particular device that's laggy? Which direction, is the problem occurring in? Upstream, downstream, what's contributing most? And is that, is the problem due to distance, link speed, or buffering and scheduling? And then how much can some of these latency mitigation technologies, whether it's WMM, low latency DOCSIS, L4S, how much can they improve the application outcomes, which is what is important to end users? And finally, if I invest in reducing latency, how can I prove that it's worked? So lots of questions, some from a customer perspective, some from a network operational perspective, and some from an investment perspective. So I'm just going to run through some of the things we've been doing in the measurement area. So if we look on the left here, we've got some of the quality standards in a simple framework there. There are lots of different standards available. These are the particular ones that we're focused on. And the foundation, the network performance measurement layer, is quality attenuation, or as the Broadband Forum has called it, as it's standardized, a range of standards in this area, QED, quality of experience delivered. So that's the basis. And then at a higher level, we've got organizations like the ITU have done lots of work on application quality of experience, and the Telecom Infrastructure Project did a lot of work on how app KPIs and metrics relate to network. And we see this metric called quality of outcome that Bjørn and Magnus have been busy driving the standardization in the ITF. That is really the glue that links the network measurements and the application outcome KPIs. And so it's a common language that app developers and network operators can use to understand the coupling between the different layers. So that's been a key focus area for us. And the thing I like about quality of outcome is that, the upper end is, per application. So you can have 100% when beyond achieving that 100%, there's no point in further spending money to reduce latency or packet loss because the customer won't notice. At 100%, they just perceive it as perfect. So some of the metrics, are kind of open-ended. You could keep piling investment and you don't know where to stop. This is very useful for that. So this is something that about 18 months ago, we did a trial in one of our countries where we were trialing quality of outcome and quality on demand. The main focus was, you can see in the middle there, it was enabling users to select which application class they wanted to operate, more optimally when they were using that, perhaps, video conferencing, working in the daytime, gaming in the evening. And that was very useful. We've actually rolled out that service now. But as one of the layers we instrumented, we included quality of outcome measurements. So on the top right there, we've got the various layers we instrumented there. At the Wi-Fi layer, the physical layer, we had all those kind of physical layer transmission parameters. We had the IP layer fully instrumented with probes in people's homes for the quality attenuation measurements. Then we had the QOO gathering on a per application basis with backend analytics. And finally, obviously, the customer's input, guided experiments, interviews, etc., to understand the linkage between these layers. And that was extremely useful, gave us some great insights. So, for example, things like video on demand, Netflix, etc., they're quite latency insensitive. Because of the way they can use buffers and rate adaptation to mask degradations in network. Whereas real-time video streaming, like live Champions League soccer games, that is a very different, set of protocols, more UDP than TCP, and shallow buffers instead of bigger buffers. Timeliness is key. But how, from a user's perspective, would they understand the difference between a real-time live video versus an on-demand? Not all users get their heads around that. And things like proof of enhancement. Congestion doesn't affect all customers. And for those it does affect, it's not all the time. It may be just in a busy hour. So how do you prove to the customer they are getting benefit? And this is where we think things like quality of outcome can prove very useful. So that was a very useful trial. But trials you can run with a few dozen, few hundred, customers, whatever, and you haven't got as immediate control over their environment as you have in a lab. So to really quantify the linkage between network scenarios and application metrics, we need a very controlled environment in a lab setup that's repeatable and automatable, so we can run through a huge range of parameters and understand how things interact and work out what's the predictable region of operation to deliver the best application outcomes. And on the top right, you can see from some of the work we were doing with TIP that different application classes have different sensitivities to latency, to packet loss, and to jitter. And the lab setup we set up in our Newbury lab enables us to control that, and we put a lot of effort into automation, and we can control congestion on the Wi-Fi, the network. We have a programmable quality attenuation degrader, if you like, that's very flexible, gives us a lot of power there. And then we can do things like, as well as understanding the link between the network and the application, we can try, quality on demand type approaches, whether that's turning on WMM or other, improvements. And we can also see what that does to the quality of outcome score and the metric thing. So that's been extremely useful, and that could ultimately lead to kind of APIs with Camara in these kind of areas to help with broadband. So going back to those questions I posed earlier, one of them is if my application feels laggy, where is the problem? So the first thing is demarcation. And for this, we've built a capability into something we call our Net Perform application with a huge amount of analytics at the back end, something we've been evolving over the last 10 years or so. This already has a range of latency measurement capabilities, including HTTPS round trip time, DNS responsiveness, ICMP, etc. And what we've been adding to this is a very simplified quality attenuation capability. to do this demarcation. And so this tool is something that runs on an app. It's crowdsourced. We can take, millions of measurements from, millions of endpoints. It's live in all our countries. The particular capability I'm focused on here, we started to roll out. That's in a couple of countries already. And the key thing here is we don't need absolute accuracy down to the nearest millisecond. This is about the relative latency. We want to know where the problem is. Because a lot of customers don't know. They say, oh, my Wi-Fi is bad when it's the network, or my broadband's, not working too well when it's the Wi-Fi. They don't, understand where things are going wrong. So this crowdsource approach enables us to do huge, massive scale benchmarking, trend analysis, etc., without any specialized hardware. And so we can quantify how many customers might be suffering from latency spikes, which network domain, and where geographically. We could even, detect, if there's a step change where there might have been a routing path change. And we can look at, the impact of busy hour on latency on these different domains. So very useful to get that high level perspective on a very, very large scale. Well, that's all well and good if we say, well, the latency looks like, the dominant problem is in the home, it's in the Wi-Fi. Well, that's all well and good, but a lot of homes these days have lots and lots of devices. It's not uncommon for homes to have 20 devices connected to the Wi-Fi. My home has typically got 50 devices connected to our Wi-Fi here. And in one trial I did, we had one customer who had 200 devices. Now, he was an IT systems manager, so he was a bit of an outlier, but that's an extreme case. But, this is growing every year. So it's no good our operations teams, our customer frontline support, identifying the Wi-Fi, it's, good or bad or whatever. If a customer's got, 20 plus devices, some of them may be working well and others not. So we want to give that capability to our customer facing teams, and ultimately to customers themselves, potentially, to diagnose, which device is problematic and why. So we've got a prototype we've developed that can do this, and we can get the full kind of latency distributions and metrics, and we could link into this, QoO type scores as well, per device, per application class. And the sort of thing we've already diagnosed with this is we had a home where, two laptops in the same room, one with good Wi-Fi performance and one with bad, and they're both on the same Wi-Fi. What was the issue? Very similar laptops. And using this technique, we could work out, actually, yes, that end user moaning about sluggish broadband or Wi-Fi, they were justified because their device had noticeably higher latency, and it turned out to be a Wi-Fi dongle or the Wi-Fi driver, I think, in that particular laptop. So we've seen the utility of this. So this is something we're keen to evolve beyond the proof of concept stage and the demos we've built. And here you can just see, this is in action. This was refreshing, measurement periods every 30 seconds. And we could see we could ingest congestion in the network or the Wi-Fi and see how that impacted the metrics we were getting out of this. So that's extremely useful. And now finally we come to the gold standard, I've called it here, the quality attenuation measurements, where we do want to get into much more detail. So quality attenuation, for those of you less familiar, is a broadband forum kind of standardized approach that can break your end-to-end latency down into the different directions and the root cause, the different components per hop, if you've got enough probe granularity there. So you can separate out what elements of delay were due to the distance, the delay, what elements were serialization delay, size of packet related, and which elements are down to the scheduling, the queuing, the buffering or buffer overload. Because it's important to understand that, because how you mitigate the latency depends on the source of that latency, which is shown in the red boxes in the middle there, different approaches that can be used. And this is something we've been deploying in one of our countries, adding to a probe capability that they already had. And we found this really, really insightful. It's given us insights that none of other tools did. So we've been able to compare different equipment manufacturers. We've looked at the impact of architecture changes on performance, software updates, technology comparisons, fiber, cable, DSL, fixed wireless access, etc. IPv6 variants versus IPv4, AQN parameters, and low latency DOCSIS before and after. And we can have, very detailed dashboards to get those insights and work out where problems are and get to the root cause. And at the moment, that particular deployment has got separate hardware probes and servers. But the focus now is a software instantiation of those, so we can deploy virtual probes that we can push, for example, into our broadband CPE. Our newer CPE is RDKB based, and we can run containers into it. And it's effectively turning the broadband CPE into like a mobile phone. We can push down functionality and containers, and that can run straight away in the CPE. And that's what the kind of thing we're looking forward to do. So in summary then, in terms of measurement, next steps, we're looking to add quality of outcome metrics to our latency measurement regime, our network quality team, our engineering team, our CPE team. We've got a lot of folks very interested in the potential here. And we're looking, as I just mentioned, how can we virtualize some of our measurement probes? And then ultimately, beyond the measurement is the mitigation. We're looking at how we transition our low latency DOCSIS and our L4S trials. We've trialed that in a fiber context, L4S and BNG networks. How can we drive that towards deployment? So that's what we're working on now. But we've also been working with some of the third-party benchmarking and testing companies on proof of enhancement, because some of them do latency under load tests. But if they're not marking their packets correctly, they won't show the benefits of low latency DOCSIS or L4S that customers are actually experiencing. So we're helping them understand that. Okay, I hope that.
All right.
That covers.
Thank you very much, Gavin. There is no extra time for Q&A here, so I think you just have to move to the next speaker. But there are a few questions in the Q&A tool, so if you find the time, please address those there, Gavin. Thank you very much. All right, next up is Lauri Alho, based in Silicon Valley. Lauri leads the global ecosystem strategy for Nokia's Network as Code platform, bridging deep tech network capabilities with the application economy, with a focus on how network APIs and AI agents drive the next generation of connectivity. So, Lauri, the floor is yours.
Thank you, Bjørn. All right, I hope the screen is visible. So, good morning, good afternoon, good evening, everyone. It's a pleasure to be here at Understanding Latency webinar. There was already some discussion about quality on demand, but let me in this presentation also go and double click down to see how quality on demand actually affects the network performance. For decades, our industry has been obsessed with a single mission, connecting people. We built networks to carry your voice, your video, and your messages. And in that human-centric world, latency was a metric we tried to minimize. It was a static hurdle we tried to overcome with a better hardware. But today, I want to talk about the fundamental shift, because we are moving from connecting people to connecting intelligence. We are entering the era of agentic AI, where software agents, robots, and autonomous systems are not just passive users of the network. They are active participants. They don't just consume connectivity, they negotiate for it. And the topic of my keynote is when AI controls the network, latency as a programmable asset, because in this new AI native future, latency is no longer just a fixed physical constraint. It's a programmable resource that developers can control, optimize, and trade off in real time. So today I'm going to show you exactly how we do that. So let's look at where we are today versus where we are going. On the left-hand side, we can see the application now model, and this is the world of over-the-top OTT applications. The application sits on the device, the network sits underneath, and there is a wall between them. The app is blind, it has no idea the network is congested, if the latency is spiking, or if the user is moving to a dead zone. Basically, the app just hopes for the best. It works if it works. But this best effort approach, it worked for humans who can tolerate a buffering wheel for a few seconds, but AI agents cannot buffer. If a drone avoiding a collision or an industrial robot syncing with a human worker needs certainty, they don't need hope. So on the right-hand side, we see the shift to applications with network as code. And in here, the application and the network are no longer strangers, they are integrated. And through Nokia Network as Code, the application gains awareness. It can see device status, it can verify location, and most importantly, it can demand specific performance parameters like low latency on demand or specialized network slices. So we are turning the network into a programmable platform. And this bridge allows developers to build applications that don't just write on the network, but interact with it to secure the performance they need exactly when they need it. So why do we need this programmability? Why can't we just run everything at maximum speed all the time? The answer is the trade-off between cost, compute, and ubiquity. So let's look at the real-world scenario, visual threat detection for drones by using security cameras in this example. So what you can see from this diagram, we have a typical setup. We have cameras feeding video into a centralized cloud AI, and this is basically agentic general purpose scene interpretation. And the AI model here is powerful. It's massive large language model or vision model running in a data center far away. It's cost effective because it's centralized. It's also always on scanning for general events. But if you look at the architecture, the video has to travel from the edge device through the radio network across the transport layer all the way to the cloud to be processed. And then the decision has to travel all the way back to the camera or the system. And this creates a best effort network environment. The latency is high, maybe often over 800 or 1000 milliseconds. And for general monitoring, that's fine. But if that camera detects a hostile UAV entering a secure airspace, 800 milliseconds is an eternity. It is low fidelity in terms of reaction time. So we cannot run high precision, low latency edge AI 24/7 for every single camera because it would be astronomically expensive and energy inefficient. So we are stuck, or at least we were. So this is a forward-leaning vision where the agent-centric network changes the game. So we don't need high performance everywhere all the time. We need it somewhere at the right time. And here we see the transition. The cloud AI, our general purpose agent, if you will, is watching the feed. It spots something ambiguous. Maybe it's a bird, maybe it's a rogue drone. The moment that detection happens, the AI agent makes a decision. It decides, I need better eyes, I need faster reflexes. And this is where the magic happens. The agent itself triggers a call to network as code. It's not a human operator flipping a switch. It's the software autonomously negotiating with the network pipeline. And it requests two things simultaneously. The first one is optimization of the network. It asks for a quality on demand to prioritize this specific video stream over all other traffic. And the second is optimization of inference. It requests edge routing to shift the compute workload from that distant cloud to a local, powerful edge computing sitting right next to the base station. And this creates a dynamic loop where detection triggers infrastructure optimization. And this is the result. On-demand agentic scene interpretation on the AI edge. So once that trigger is pulled, the architecture changes instantly. We are no longer routing to the cloud, we are routing to that local edge. And we have moved from a general purpose high latency model to a specialized high fidelity model. And because we are now processing data on a local GPU at the edge, and because we have prioritized the 5G traffic, our latency drops dramatically, down to 200 milliseconds or less. So in essence, we have bridged the gap between cloud reasoning and edge precision. And this allows for sensitive workloads, maybe like real-time tracking of a fast-moving threat, to be handled with absolute precision. But crucial to the business case, this is on demand. So we are optimizing the monetization of the infrastructure. We use the expensive high-power edge resources only when the threat is active. And when the thread is gone, the agent negotiates the network back to its low-cost state. So this is latency as a programmable asset. You pay for it only when you spend it. And now, maybe rather than just talking about diagrams, I want to show you this running live. So next I will show a recording of the system we built and demonstrated live at the NVIDIA GTC event in Washington, DC. And I will walk you through exactly what is happening in the network logs and dashboard as we switch from human-centric to agent-centric control. So let's roll this low latency video, if you will. So this is a demo recording of a live edge routing where we solve the critical trade-off between cost and immediacy. Right now, the dashboard is in efficient mode and object detection is running in the cloud, but look at the latency, over 1000 milliseconds. Too slow for real-time threats here. I'm switching to agent mode to let the AI take over. I'll instruct the agent to look for UAVs and consider those as threats. As a drone enters immediately to the camera 1, the agent detects the threat and instantly triggers the network APIs. Quality on demand prioritizes the traffic, and edge routing shifts processing to the local edge compute using NVIDIA GH200 GPU. The orange box shows the latency drops to 200 milliseconds, giving us high precision tracking and ultimate validation of the potential threat. Now, what's the adaptability? As the threat clears, the system runs a 10-second cooldown timer. The edge switches off to save the cost, but the moment the drone returns, the agent will re-trigger the edge instantly. No manual intervention, just precision on demand. And here we can see the logs of the agent running the network as code API calls. Here we see the successful quality on demand API call with all the necessary details, and this second successful API call requesting the edge routing API. So this is the AI native future, turning the networks into an intelligent platform, already live demonstrated at the NVIDIA GTC DC at Washington, DC. So what you just saw is the future of our industry. We often talk about smart networks, but truly intelligent networks are the ones that can be commanded by the applications that run on them. And by using network as code, developers can finally bridge the gap between the infinite reasoning power of the cloud and the immediate physical precision of the edge. We are moving from a world of static SLAs to dynamic agent-negotiated performance. And whether it's for industrial automation, autonomous logistics, or public safety, the network is no longer just a pipe. It's a programmable asset that adapts at the speed of AI. And at Nokia, we are building this AI native future today, and we of course invite all of you to build it with us. So thank you very much, and now back to Bjørn.
Thank you very much, Lauri. There is a question here. The question from Michael Richardson is, so how is the trust between the camera and the network established? Is this via an ISP orchestrator, some host to network API, or is it a problem for the ISP to be vertically integrated?
How I'm understanding the question is, or if we think about that architecture, there is a camera, like in everyday use today, using 4G, 5G subscription. It is already sending that encrypted video feed over the CSP network to the cloud. And in the cloud, we can run secure network as code quality on demand API call, which means that the cloud computer connects to our Nokia's globally hosted network as code global backend system. And from there, with the phone number information, we can route that quality on demand call to the right network, into the right CSP network in which the camera is being operated. And that is, of course, all secure, authenticated, consent managed API call. So when that reaches to the operator systems, the operator's 5G systems understands that, hey, we need now to change the quality of service parameters and eventually, for example, prioritize the traffic. And from the camera, there isn't actually any interaction with that underlying BSS or OSS systems directly that the CSP has. So it happens through Nokia's global platform. And then when the change happens from sending bits from camera to the public cloud, going to the edge AI, then of course, once again, there is secure transport layer to move those bits over there. So I hope this little bit answers to that trust question between the camera and the network which it's being using.
Right. Thank you very much. And with that, we'll move to the next speaker. Our next speaker is Ali Begen, a computer science professor at Ozyegin University in Istanbul and the founder of Networked Media, an innovation and engineering studio focused on IP video technologies. Ali has worked across academia and industry, including as a technical lead at Cisco, and is widely recognized for contributions to streaming and media systems. So, Ali, please go ahead.
All right. Good evening and good afternoon, good morning. My name is Ali. I'm going to talk about MOQ transport as the NIF standard that we have been working in the IT for a while. The only thing that is AI related is probably the AI, the little AI here in MOQtail, which is our own implementation of MOQ. It's an open source reference implementation, and I'm going to give a couple of pointers, what we have seen as we have been developing that for a while, and what we are planning to do next. So, all the stuff on my website, personal website, and there's obviously all the nice things about MOQ on MOQtail.dev website. So, it's not really maybe very much needed for this crowd to explain the latency, but when it comes to streaming media, latency, is a delicate topic. So in 1969, I wasn't even born at that time, but apparently the largest, the biggest broadcast event has happened when mankind has landed on the moon. So, the astronauts on the moon, they were broadcasting, live video from the surface of the moon and over 250,000 miles away. And then it was less than 3 seconds. And 50 years later, Super Bowl 53, which was in Atlanta, where I went to school, we had all these technological advances. But then even if you were just a couple of miles away from the stadium, the latency will be about 45 seconds. And you think that maybe 2019 was bad and things have improved, but not really so much. So these are the statistics from Super Bowl earlier this year. And frankly, I'm not really expecting too much improvement in February, in a couple of months for next year. So, the over-the-air broadcast was about 20 seconds behind live action on the field. And the fastest or the lowest latency platform was Tubi on Fox TV, because that was the primary broadcaster this year. It was 26 seconds, so it was still several seconds behind live point. And all the other major platforms, they were way behind the action on the field, which maybe very important to some people, but then for a lot of use cases, latency is quite critical. Now, it is not that we don't know how to make this work. As a matter of fact, I've been one of the lucky guys who started working on this low latency live streaming problem back in late 2016, early 2017, and then we started developing the spec, the demo, and then everything. And then we even wrote published papers and did the implementations and things like that. And all that stuff is already known. So you might ask the question why it's not really widely deployed. Well, there are still some fragile points, and unless there's really a huge demand from the market, from the viewers, probably that's never going to happen. There are some limited deployments, but not really too many. So when we look at the latency scape, we have all kinds of media applications and all kinds of different streaming protocols. So for high latency or typical latency, as I call it, anything beyond 10 seconds, we have Dash and HLS. They have been running for almost 2 decades now, in the field. And with varying segment sizes, you can get latencies tens of seconds. If you want to do some low latency because your application requires that, because maybe there's some esports component or there's some social media component in it, or you want to be really on par with the traditional broadcast, you need to come down to less than 10-second latency. And then for those, we have low latency dash and low latency HLS. Again, these have been out there for a while, but things are a bit more fragile with these extensions, and that's why we don't really have too many deployments. But then if you are really at the real-time edge, or you are really looking for ultra-low latency, WebRTC has been the de facto protocol so far for all these drones, video conferencing, cloud gaming, and so on. And then somewhere in the middle, as you can see, between a couple of seconds, around a second latency, there hasn't been really a nice and a versatile protocol that can do all those nice things for us. And then that's why, exactly 3 years ago, we had our first meeting in the ETF, Media Work Quake, and now we just call it MOQ. The meeting, and then since then we have been working on developing that. Now, MOQ was supposed to address only this little, space in the entire spectrum, but then, soon after we started working on it, we realized that actually we are developing such a versatile protocol. We can do all the nice things that WebRTC has, and then all the nice things Dash HLS have as well. So rather than dealing with all these issues with related to WebRTC or Dash HLS, we can actually have a really nice protocol which is media agnostic, and then we can cover the entire spectrum. So you deploy a single MOQ CDN, for example, and then you can cover pretty much any application you want to. Now, this work is taking place in the IETF, and then here is the basic diagram for it. So we have a component called publisher, which is sending media, and then on the opposite side, we have a subscriber receiving the data, and then both sides could be publishers and receivers at the same time, publishers and subscribers. And then in between, we have these relay components, one or more. And these are going to be part of your CDN, content delivery network, and then they're going to establish all these fanouts and for large scale streaming and for caching purposes and so on. We have media tracks going from publisher to subscribers, and then we have a bidirectional control stream between the subscribers and relay, between the relays and between the upstream relay and the publisher. Now, the transport can be web transport in a browser environment, or it could be just a raw, quick connection. And the interesting part, all the components we need so far are pretty much already available, with the exception that web transport is still being finalized. It's going to be in RFC pretty soon. But the challenging problem, the interesting problem for people like me, coming from the research domain, are these rate adaptation and congestion response strategies. So how we are going to react to all the things happening inside the network when we are transmitting some real-time media or low latency media or on-demand media, right? All those things will affect how we are going to change our transmission priorities and things like that. And MOQ gives us all the tool set, but what you are going to do with that tool set is really up to you. Now, the nice thing about MOQ, as I just mentioned a couple of slides earlier, it's really about combining all the media use cases. So it could be on-demand streaming, like Netflix type of thing, or it could be real-time, like sports betting or esports, or just regular live streaming, right? It will be a single protocol that can support both with the subscription model and the fetch model. These are all integrated APIs into the MOQ transport. I've been working on Dash since day one, and if someone just asked me to replace Dash with yet another streaming protocol, I wouldn't be really too much, excited about it, or replacing just WebRTC. But when it is something that will replace all these different protocols into a single bucket, I really got excited about this. So, my students, my colleagues, we are working on a number of problems, on a number of research, issues, which I listed here. Obviously, these are really detailed topics, but you can You can have a look and see whether there's an interesting thing for you. And if there is, then please join the discussion. I would love to talk to you about any of these topics. These are the things that will determine, how successful mock deployments will be. Now, one of the things I'm going to talk about MOQtail, which is our open source reference implementation pretty soon. But one of the things we realized when we started working on this was, the best thing about mock is really this unifying abstraction. So it could be a real-time media application, just like what we are doing here, using Zoom or WebEx, right? Or it could be just a streaming application like a Netflix or YouTube and so on, or anything in between, right? So mock is going to support all those use cases and the message types, message parameters. Yes, there are so many, but then, a single framework, a single abstraction layer is going to give you all the capability you need. You don't care whether it's HD content or HDR enabled content, or it's VP8, VP9, AV1, VBC. You really don't care. There are proper packaging formats for all of them, and mock is really agnostic to any of them. And mock is optimized for latency. Subscription model was inherently designed for that, but then it also supports all the other use cases too. The nice thing about mock in terms of latency is latency is tunable, so you can adjust it for your needs. And if you are really in a bad network, in a poor Wi-Fi network, for example, you can slightly increase your latency so that your streaming performance is still not affected at least too much. And then simplification of infrastructure. This is also a nice feature. Since it's going to be a single protocol, if there will be some mock CDNs, which I expect them to become available in the next year or so, you can use the same CDN for real-time video applications like Zoom, WebEx again, or you can use them for streaming purposes. When there's Super Bowl, you can stream that. When there are people are watching Netflix movies, you can stream those streams as well. So there are 6 different demos on our website. I just want to emphasize this one for a second. This is time travel demo. This is basically a video conferencing application that we built on mock. It's just a regular web conferencing application like screen sharing, audio, video, chat, and then everything. But on top of that, there's also this rewind capability. So if you miss something important in the meeting you are attending, you can, at that time, you can just scroll back, play what you missed, and then, maybe answer any questions, or maybe, really figure out what's really happening in the call and so on. So maybe you missed the first 5 minutes and so on. So this is really indeed nice feature, not really available in WebEx or Zoom. Recordings are always available after the event is over, but we make them available in our relay infrastructure where real-time media exchange is happening. We also provide on-demand capability. So if you go to our website, this is what you're going to see, moqtail.dev/demo. Unfortunately, I don't really have the time to go into details of these demos, but there are GitHub repos and some papers, some presentations about each of them. Some reports are coming out, which we are still working on. So feel free to contribute and raise issues and so on. So with that said, that's all. Please visit our website and let us know what else we can do. Thank you.
Hey, that's a super interesting, Ali. I have a one question here.
Yes.
So Satish is asking, is there a problem that publishers can flood the network in this architecture if
Well,
there aren't enough
if they want
subscribers?
to, they can certainly do that. But then publishers are going to publish something if there is someone asking for that, right? So if there are no subscribers, if no, I mean, the relays are not going to ask that stuff from the publisher unless subscribers are asking for it, right? If you just want to flood the network, you can always do that, but that's really not really a more specific issue, I will say.
Makes sense. All right. And kind of an unrelated question, actually, but someone's asking for why the chat between attendees is not working. And I think we've just misconfigured it, and we tried to fix that, but we don't know how to do that live. So we'll try to look at it for tomorrow. Sorry about the chat being missing, guys. Okay,
well, if there are any questions specifically about mock or MOQtail, just email me. Thank you.
Yeah, and also the Q&A function is working, so please add your questions.
I'll have a look. Yeah. I'll have a look.
Right. Thank you very much, Charlie. Up next is Jose Lopez, CEO at Bequant. And Jose works on algorithms to reduce latency, improve quality of experience, and provide network visibility technology that's deployed in hundreds of ISPs worldwide and use TCP optimization and machine learning to detect and mitigate congestion in real time. So Jose, welcome.
Thank you. Thank you, Bjørn, and thank you also to Victoria and to all attendees for their interest. So we would like to present a proven way to reduce latency in internet service provider networks and a way to multiply the usage of L4S, which will lead to even lower latency. All this using an L4S TCP proxy and machine learning algorithms to detect congestion in real time and apply active queue management in those congestion situations. So buff bloat, or excessive latency, as we all know, occurs when there is a bottleneck, that is a capacity limit or a rate limit being enforced. If you send packets at a higher rate than the bottleneck limit, packets will have to wait in a queue, and that waiting time will be the added latency. That queue fills up, packets will also be dropped, forcing the sender to retransmit them and making things even worse. And all this is what we want to avoid. So what can we do? We basically have to add intelligence to the sender and to the device where the bottleneck happens. We should start by implementing some kind of fair sharing for the limited bandwidth at the bottleneck, so that the packets of applications like real-time video and voice or online gaming don't have to wait in the queue in the same line as the packets from video streaming or software updates, which don't care much about latency, but you use a lot of bandwidth. Fair queuing algorithm at the bottleneck will help tremendously, because even though the overall latency will still be the same, the latency experienced by applications that really suffer from latency will be much lower. But the way to reduce the overall latency is to force the sender to match the rate limit at the bottleneck. If the sender transmits exactly at that rate or below, no queue will build up. Just like when you pour liquid into a bottle through a funnel, if you pour at the right rate or below, it will not accumulate in the funnel. And so the sender rate is determined in the server by TCP or QUIC. Since almost the start of internet, that was done using loss-based algorithms, which kept sending faster and faster until they flooded the queue in the bottleneck, which caused packet loss, which they detected, and then started sending slower. But they kept probing and driving the queue to drop packets over and over, and that was horrible for latency. But in fact, it is still being done by the cubic TCP algorithm, which is the default still in Linux TCP. Fortunately, rate-based algorithms have appeared since then, like BBR, available for Linux TCP and also used by QUIC, or are on Bequant TCP and others. They determine the right rate to send without swamping the bottleneck. Many senders now use these new sophisticated algorithms, and that has helped reduce latency to a large extent. But there's more that we can do. We can add more intelligence to the bottleneck, in addition to the fair queuing that we mentioned before, implementing an active queue management algorithm so that servers can determine the correct sending rate faster. AQM algorithms like, for instance, FQCodel, CakePy, and others that we will also be hearing in this conference detect congestion and in the queue and drop packets before the queue is overflowing. In the sender will detect those drops and slow down when a queue builds up, but before it reaches to high latency. So when present in the bottleneck, these AQM mechanisms can often significantly reduce buffer bloat. But in fact, as many of you know, these AQM algorithms will work more efficiently if instead of dropping packets, they mark them. For example, if the sender, the client, and the bottleneck support ECN, explicit congestion notification, a fairly old IETF standard, the bottleneck can signal congestion, marking packets. The client will get those marks, will relay those to the sender, which will then act appropriately, and thus avoiding both high latency and wasteful retransmissions. And finally, we have L4S, a more recent standard, which combines all these aspects, adding a very accurate way of signaling congestion with an improved ECN and enabling very low latency. So if we have all these pieces of the puzzle, why do we still have high latency in the internet? Why do many gamers still complain, and why are many video conferences frequently a bit of a nightmare? Well, first, there are still many cubic servers in the internet. It's standard for cubic. Cubic is a standard for Linux. Then, when you have different TCPs, variants, and quick sharing a bottleneck, sometimes the rate-based versions, the most modern ones, will overwhelm the cubic flows, and other times the cubic flows will drive the latency up for all the rest. Then there is unfairness towards flows coming from further away. Connections from closer by will normally take an unfair share of the bandwidth at bottlenecks. And also, there are still very few ECN clients and servers. We are in around 600 ISPs around the world, and we only see ECN in about 10% of the flows, and even fewer L4S flows, less than 0.5%. And finally, there are many bottlenecks without any advanced queuing management or fair queuing, no AQ. So many of these problems can be solved if we install a transparent TCP proxy in the access network of the ISP. It will transparently terminate the connections from the servers and serve the content from inside the ISP to the clients. So if it uses rate-based TCP, then there will be no more cubic in that network. And in fact, not only that, but no more competition between different TCPs, because all of the connections will now be using the same rate-based one, which is in fact pretty much very similar to the one used by the quick flow. So everybody using the same algorithms will make things much better. And there will also not be unfairness with towards connections from further away, because they will all be coming from that proxy server. And finally, as long as there will be more ECN and L4S. Why? Because as long as the client supports ECN or L4S, even if the server does not, the proxy can support ECN or L4S, at least in the connection leg from the ISP to the end user, which is in fact the one that really matters. In this way, multiplying the usage of L4S and ECN. And so, of course, you should use a well-proven TCP proxy, because there have been some very bad TCP proxies in the past. But for instance, there are some that work very well. Ours, for instance, has been used for over 8 years in more than 600 ISPs. And when there is congestion, you will also get some acceleration, around 20% or more, TCP applications, which constitute from 50 to 80% of all traffic. And regarding L4S support, it is very important that not only to support it well, but to support well the scenarios in which the bottlenecks do not support L4S or ECN, or just classical ECM, because in fact, those will be the most common scenarios at the beginning. So how about the remaining problem we talked about, the fact that many network nodes that can be bottlenecks, like many existing Wi-Fi routers, do not support AQM? even that can be solved also by with automatic congestion management, or ACM, which is a mechanism that we have developed and that I can explain. So the ACM functionality monitors the speed, the latency, and the packet retransmissions of every user in the network every few tenths of a second. It then uses real-time machine learning, reinforcement learning algorithms to detect when a user is reaching a congestion situation, maybe caused by an old Wi-Fi router, say at 15 megabits per second. And at that point, it enforces a rate limit slightly below that rate, say at 49 megabits per second. And if it sees that that reduces latency and retransmissions, it then looks for an optimum speed, probably at 48 megabits per second, 49.5, and so on. If at any point it sees that enforcing the rate limit does not reduce congestion, it stops messing around. In this way, in many high latency situations, ACM manages to become the bottleneck instead of the original bottleneck, which was probably did not have any AQM. Now it enforces a slightly lower rate limit, but it will be a bottleneck, this new one, using the most advanced AQM mechanisms, that is L4S, supported by at least the client, or ECN, and FQCODL with enhanced QM mechanism. Also, the TCP servers does no longer needs to find the bottleneck speed, because as a proxy, we are the TCP server and we already know it. And as a result, a much lower latency will be obtained. So to finalize, how do we see this works in a real network? Here we have and the results, 1 day of traffic for a network in the US with both fixed wireless and fiber customers, around 10,000 of them, with a peak throughput of around 25 gigabits per second, which you can see in this chart at the bottom. And the top one has a blue line for congestion percentage in that network, which is a measurement of hours that we derive from a latency and retransmission. And then in yellow, we have the amount of traffic that is experiencing ACM, which basically was turned off until sometime in the night, and then we turn it on at that time together with the TCP proxy. And at that time, we saw in this, we can see in this second chart here, how the average latency for all users in that network went down by around 40%, from around 25 milliseconds to 15 milliseconds, and how the average retransmissions over time, which measure also packet loss, went down by around 50%, from 2% to 1%. So to summarize, we've shown how a rate-based TCP proxy with active queue management, together with automatic congestion detection, can substantially reduce latency and losses today, and even further if L4S is added to the access network. And so we end our presentation here and turn to any questions that you may have.
All right, thank you very much, Jose. There are a couple of questions. So Sebastian Möller is asking, how does a proxy deal with TLS or encrypted connections?
Oh, TLS and encrypted, that happens on top of TCP, so that's not a problem. They are the same as non-encrypted connections for TCP.
All right, and then Arpad Jordan is asking if this TCP proxy can be implemented as part of a virtual BNG. And I'm going to add on that, like, where do you usually deploy them?
You deploy them as centrally as possible in the network, and near the point where a certain segment of the network goes to internet. So as to, if you deploy them too close to the end users, then you need a lot of boxes. However, if you put them centrally, you can have 400 gigabits per second or more performance from one deployment. So they have to be in the path, but as centrally as possible to reduce costs.
Thank you very much.
Thank you.
And next we have Avery Pennarun, CEO and co-founder of Tailscale, a company focused on making secure networking simpler with a zero trust, easy to use approach. Avery is known for a very practical philosophy. Technology should be powerful, but also easy to use. And he's built a lot of tools that reflect exactly that. So Avery, please take it away.
All right. Can we see my slides?
We can.
Excellent. Okay, so I'm gonna, this is probably gonna be a little different from the other talks you're seeing today, because I'm mostly gonna complain about stuff, and I'm not gonna present any tools to you that make anything easier to use. So don't worry. I'm Avery. I think I got first invited to speak at this conference 2 years ago because I was doing some research into latency reduction in Wi-Fi systems, which is like serious engineering. There was like fair queuing and Codel and scrubbing double-digit milliseconds down to single-digit milliseconds. That's the sort of thing you'd expect to see here. Nowadays, I'm at a higher level of abstraction, and I'm getting more frustrated by the hundreds of thousands of milliseconds of latency that just don't need to be optimized. They need to be removed altogether because there are whole entire subsystems that are actually just dumb that should go away. So I look at things from the systems level, which is maybe a little different than what you're used to seeing around here. My talk here, you guys are all over the playground rearranging packets, and you thought latency was bad. Here's the news. Here's the longer version of my title. That didn't fit in the description. So you thought the latency was bad. Well, it is for way too many reasons, and it's getting worse because we suck at fixing things now at a horde of AI agents. So it's trendy nowadays to include AI and everything, so I thought I'd throw that in. The AI angle makes our investors happy, but otherwise it's not going to change the story very much. Other than if you empathize a bit with the poor little bots, it's actually even worse for them than it is for us. How did we get here? I like this quote. This quote guides my life. We can solve any problem by introducing an extra layer of indirection, except for the problem of too many layers of indirection. And that's attributed to David J. Wheeler, but there's like 5 other people that also sort of get credit for it who all quoted each other at different times. It's a quote about bureaucracy, but it's especially about bureaucracy in computer systems. We've spent years not fixing any of the underlying layers and trying to work around the problems with even more layers of indirection. And it's now reached epic proportions at the systems level. Let's rewind back to the beginning. Published in 1984, although it took several years before that before they could publish it, we have the OSI stack. Now, I love the OSI stack because it's famous for essentially never having been implemented by anyone in any real system. I took a networking class back in 1999 when I was at university, and the professor was already saying this model's obsolete and wrong, but it's what's in every textbook and it's what everybody talks about. So let's relate all of our networking stuff back to that. And that's what we've been doing for decades since. We hear about layer 7 pretty often. It's called the application layer, but we have proxies at the application layer. How is that the application layer? Not sure. Nobody ever talks about layers 5 and 6. They're imaginary. And then we kind of smush layers 3 and 4 together on the internet. But it's not all bad. My favorite layer is layer 1. It's the good layer. It's analog. It almost never adds any latency except for the really serious stuff, the speed of light or whatever. I can respect layer 1. Everything else relates back to this other quote that I really like. When a hardware engineer's system fails, he takes comfort in knowing there's a rational reason because the universe was created by God and God is rational. The software engineer has no such solace. And the reason, of course, is that the hardware and other software systems are created by humans, which are definitely not rational. Even if you don't believe in God, you can sort of believe in the rationality of the laws of physics, which all of the layers of the internet are not, except for beautiful layer 1. It's all our fault, one way or another. We've built this mess that adds latency everywhere. And the OSI stack has never been implemented. The real stack, I'm not sure anyone has ever successfully drawn a diagram for what we do instead of that. Here's the start. First of all, this one's a little more real. We definitely have physical layer 1 still. That's not going anywhere. There's no doubt we have layer 2. Those Ethernet MAC addresses are everywhere. Remember when we used to think Ethernet could be a bus topology? And then we gave up because we couldn't get Ethernet's useless collision protection heuristic to work at high speeds. So then it was a star topology. So you'd run these giant bundles of Ethernet cables through a whole office building, 1 cable per computer, just because we couldn't figure out how to multiplex several computers onto a single cable at layer 2. In retrospect, that was actually super embarrassing. I mean, just think about it. You could wire things physically together, but you couldn't actually make the protocol work on a single wire. Amazing. Right? And here we are today with cellular and Wi-Fi. And you know what that is? It's Ethernet back in a bus topology, a big shared medium, right? We have all the Ethernet MAC addresses, and we've now tried at least a dozen different collision avoidance mechanisms, and it sort of works as long as layer 2 retransmits packets when the collision avoidance didn't avoid, so that the packet loss doesn't leak into layer 3 and 4 and confuse them into thinking it was congestion. Anyway, that was a digression. So layers 1 and 2. On the other end, we have layers 4 to 7, which have now all been jumbled together in HTTPS, which now includes QUIC, which means it includes UDP. You want to send stuff in a browser? Sorry, no socket access. You're sending it through HTTPS jumble. It's not UDP, it's WebRTC or WebSockets. We added layers to solve our problems, except for the problem where we have too many layers. And then in the middle, we've got layer 3, which is Internet Protocol. And I'll point out that we also kind of botched the Internet Protocol because it no longer does the one thing an Internet Protocol is supposed to do, which is give every device a fixed address, no matter where it plugs in, so you can actually reach it. When you think about it, that's actually pretty weird. Layer 1, everything has a fixed address. It's the wire you plug it into. Layer 2, everything has a fixed MAC address. With HTTPS, everything has a fixed URL. But at the internet layer, the one that's supposed to make it possible to address everyone everywhere, you don't have an address. It's like if my name changed every time I moved houses. How do we fix that? So how do we fix it? The answer is even more layers, but this time we're going to stick them onto the side, right? Side layers and detours. Just look at these. Nothing today works without these things we've jammed onto the side of the stack. I can't even find what IP address to use without DNS jammed on the side. And then you get these memes about it's how it's always DNS. That's not a coincidence. DNS isn't even part of the stack in the first place. It's an afterthought. IPv6 never got fully deployed, so not everything has an IP address. That means clients are typically behind a NAT and a firewall, so now all they can do is talk to servers in the cloud. If I want to send a file, it goes to the cloud and back, even if my two computers are sitting side by side connected to the same Wi-Fi. That's really sad. Layer 3 failed us, so we fixed it at layer 7. And then, oh, how do I know the device connecting to me is really the one it says it is? Physical wires, those were nice. Remember, once upon a time, light bulbs used to be 100% sure which light switch controlled them because we wired them together. Well, nowadays we solve it with encryption keys and tokens. To get the right tokens, you need OAuth2, another side protocol. OAuth2 doesn't work without HTTPS, so it's a layer on top of HTTPS, even if all you wanted was just some UDP, right? I tried to do a block diagram for this slide, but it's kind of like a little spiral. All the layers of the stack just connecting to all the other layers of the stack. Why did I include serverless containers and distributed databases in the list? Well, because they're the new thing. You want to abstract away physical computers now, just put your container wherever and we'll find our way to it. Neat. But layer 3 is useless at that too, so back to layer 7. And distributed databases, same idea. Why do you want just one database when maybe that database isn't close to you? Or it might go down. So let's run lots of databases and they're going to sort out how to be in consensus. Well, that adds latency. Everything, all of this stuff adds latency. And it's all on top of the network layer that we've been scrimping for milliseconds down at layers 2 and 3, right? That's tiny by comparison. And then AI agents, just like one step up, is kind of depressing. But the world we've left for our children to inherit, the one we just talked about, or our bots, right? Our bots, like our children, have an added problem, which is we absolutely don't trust them to do anything on their own. It's basically helicopter parenting for computers, right? When I was growing up, by the time I was 4 years old or so, my parents could just kind of shove me out the front door and trust that the neighborhood kids or random people in the street would take care of me, and it was fine. That reminds me of our attitude to network security back when we invented Telnet and RSH. Now it's different. No trust. The security people would say zero trust, but zero trust for people. For AIs, it's negative trust. Look at Claude Code. It's literally installing a remote code execution vulnerability on your computer to try to make you more productive. Security teams don't like that, so they're clamping down. How do they clamp down? They clamp down by adding layers on top of layer 7, right? The only layer we know how to add are on top of layer 7. So it's proxies all the way down. A proxy between Claude Code and Claude, a proxy between OpenAI and your MCP server. We're not even sure what to put between your computer and the tiny random SaaS companies that are asking us to upload all of our customers' private data to them so they can analyze it. It's probably also a proxy. And because it's AI and we like spending money, we're going to have another AI watching the data stream from the proxy and to see if anything's going wrong. Which brings us to the ancient question, who's watching the watchers? More watchers. Every single one of these things is more latency. You can bet not all of those proxies and watchers are conveniently located close to you. So it's interesting to see how people try to resolve this latency problem. On the web, the classic solution to high latency is to add more parallelism. It takes too long to load one HTML file and JavaScript at a time. Load 20 things at once. It's okay, it helps, but it has limits. For AIs, the parallel is subagents. One agent takes too long because there's too much back and forth. Okay, do a whole bunch of things at once, then put the pieces back together at the end. There's a parallel there to human teams. You know what has really high latency? Talking to other people. One of my least favorite things to do is talking to other people. It takes me right out of the zone. Plus, they have ideas and feedback and stuff, and they make me throw away my work and start over. I can't make talking to people more pleasant, but if I can do it with more latency and faster, at least I'll throw away less work. And that's the same problem AI subagents are facing, but times 1,000 because I can hire 1,000 subagents, right? What does it feel like when web pages are slow to load? Now imagine you're an AI agent and to do anything, you have to do 50 of those to form a single thought, right? Imagine if every time you wanted to open a file and see what's in it, you had to do a round trip through all 7 layers, plus a proxy server with 7 more layers, and an AI inspector with 7 more layers, watching your every move. It sucks. If we care about the AI's feelings, it's our responsibility to do something about all that unnecessarily systemic latency. So there's all kinds of things we can fix. I think, I would encourage people to look at things at the system level and see how we can get latency down by an order of magnitude across the entire system, not just the packet level system. All of these things matter, right? Not just layer 2 and 3. We can make such a huge difference just by fixing our systems. It involves going back to the layers that people haven't wanted to investigate now for years or decades, right? It's going to not just help AIs, it'll help humans too. Can we get our servers closer to our clients? Why do I have to log in so many times per day? And why does it take so long each time I do it? Why does a simple API call have such a long setup time? And why is the answer something about Ruby on Rails and something else about serverless functions? Could I eliminate a whole bunch of inspection points just by establishing a higher level of trust across the board? Isn't trust what society is supposed to be all about? And what does it mean to our society that we've reached the point that zero trust is the actual stated goal of systems design, right? I don't know the answer to any of those questions, but I will take some questions in the next 5 minutes. Thanks, everybody.
Thank you very much, Avery. That was a very fun talk. And now you have to talk to some people, I'm afraid.
Excellent.
I have a question to start off. Do you have some examples, like with numbers, of the phenomena you're describing in this talk?
I mean, I have many examples. The numbers are so high and variable that it's almost not worth measuring, right? Like when you look at layer 7 proxies, a common thing to do is put especially with AIs, where GPUs are so expensive that people will often route to wherever the GPUs are cheapest in the world. So you can talk about world spanning just speed of light latencies, plus extra layers on top, establishing HTTPS sessions and so on for multiple things every single time. They will connect and disconnect. They'll all kinds of random delays. So you're talking about thousands of milliseconds sometimes.
Makes sense. All right. Any other questions in the Q&A? I don't see any questions right now. People are saying it's a brilliant talk, no questions.
All right. Well, I'm going to take that as a positive then.
All right.
We're just going to sit here, for the next 3 minutes unless you ask a question. We can't be ahead of schedule. That would be negative latency.
It's totally okay to be ahead of schedule, but yeah. Yes, there it is. Hi, Avery. Any thoughts on RENA, recursive internet architecture? Seems to have a similar view on layers.
Oh, yeah. Someone sent me that link like 5 years ago, and I have been inspired by it ever since. I've been trying to write a blog post in which I describe, like, there's actually a missing layer, which is like the sort of the topic that they had in between layer 3, 4, which is the internet, and the thing that actually is supposed to do layer 3. As I've been thinking about it over the last 5 years, I sort of realized that, ironically, IPv4 or IPv6 are actually doing the job of layer 2, which is a really weird thing to say. Like, the thing we don't need is MAC addresses, but then you put in an IPv6 address, for example, and now everything has an address that corresponds to what it's plugged into, which is what you'd expect at layer 2. But it totally fails to get you an actual permanent address of your device that works everywhere. So you're actually missing the internetwork layer. And you can solve that by putting a little tunnel in the middle, right? Which of course is what my company does. But it's interesting, like, there's many different ways to do it. But philosophically, we're missing layer 3. And the fact that we're missing layer 3 has led to a series of just like hack upon hack upon hack upon hack upon hack all the way up the system. And if you can just fix that layer 3 properly once and for all, you can eliminate layers and layers of hacks. And the RENA project is like, basically they were the first ones to identify that this is the problem. And it's funny that they identified it using, I think, a rule of thumb, and I forgot who first said it, but from like years and years before that, like from one of the earliest discussions about the internet protocol, they realized this was a problem, that we'd assigned addresses based on what you're plugged into instead of the identity of your host, and that this was going to be a big disaster. And it turned out, it was, but we didn't listen to them at the time.
Yeah, it's an interesting history how these things have been developed, and it's like layers on layers, both kind of technically but also historically. Like we've just built stuff on the old stuff all the way.
Yep.
Yeah.
Layer 4, by the way, is the only layer that doesn't uniquely identify a device, which is super weird, right? Normally you would have like, and with Quick you have a unique identifier, but like a UDP port is like 16 bits. It's definitely not enough to identify a device, and that's why your device can't move around without breaking your UDP sessions. But
Right.
again, a violation of the theoretical basis for layers.
That's a very good point. Okay, thank you very much. That gets us to the break. So we have 10 minutes break. We'll be back at past. And again, thank you very much for speaking, Avery.
Thanks, everybody.
I'll try to bring up my pause screen here. I think you're... All right, I'm gonna hope that's working. All right, we are back. I do think, however, that we've kind of set aside a bit too much time for the for the sort of after break intro. But let me just show, let's use a little bit of this time to show what we are going, what's coming up. So we have this is a 3-day event, as I'm sure you are already aware. And today we still have Dean coming up, and Jeremy, Frank, and Duncan. And then tomorrow we have Jason Levigood from Comcast. We have Cohen the Shepherd from Nokia Bell Labs. We have Lai Olsen from Cloudflare, Greg White from Cable Labs, Jonathan Newton from Vodafone and the Broadband Forum, Stuart Cheshire from Apple, Wim de Ketelare from Accentis, and Mohit Tahiliani from NITK Surat Kal. And so that's tomorrow, the Tuesday. And then on Wednesday, and the final day of the event, we have Michael Philpott from Omdia. We have Nick Fimster from Net Microscope, Kerry Baker from Ookla, Alexandru Chinaru from Orange, Josh Hardy from Orb, Magnus Olden from CUJO AI, Sandeep Singatvaria from Meta, Tim Evans from Cisco, and Eric Bertrand from Comcast is finishing off the event this year. All right. And I think it's okay to just start a little bit earlier than planned, Dean. So let me just find my notes and I will introduce you. So welcome back, everyone. Our next speaker is Dean Bubbley, founder of Disruptive Analysis, an independent technology industry analyst and consulting firm based in London. Dean has spent 25 plus years connecting telecom technology choices to the broader realities of user experience, markets, and policy. So Dean, over to you.
Thanks, Bjørn. So I'm going to do a quick roundup of something which is a bit different to the other presentations we've had so far. So rather than looking at the technical solutions for mitigating latency, I'm going to try to introduce some of the physical world and network factors, as well as some AI considerations, which will determine whether and how and where we can control latency. Because I think that it's easy to assume that we have a nice predictable setup of user against network, but I think there's various reasons why we might need to think about it a little more carefully and model our scenarios to be dynamic to really the real physical world. So as you mentioned, I'm an industry analyst and advisor. I cover a bunch of different stuff. So on the network side, I look at everything from wireless networks and spectrum policy to fiber and telecom operator strategies. But I also do quite a lot of work looking at specific areas such as voice and video communications, and also the realm of AI, edge compute, and some work on APIs and sort of AI intermediary layers like MCP at the moment. And I'm also sort of thinking about some of the more futuristic applications where you may have multiple workloads involved in a single larger object or use case, such as robotics or aerial vehicles. So for me, the key point here is where is the user or the end device? And specifically, are they indoors? Are they outdoors? Are they moving? Are they static? How predictable are they? And is your latency going to be dependent on other physical effects such as radio interference, for example, which will determine the quality of any connection that you can get if it's say a cellular or Wi-Fi or satellite link. Another important thing here is the plural, is which networks potentially is something connected to, either in tandem, where you've got things which are connected to multiple networks simultaneously, or sequential, where you have multiple hops. And so even though you may be able to manage latency across one part of the connection to the end user, the question is how you then glue that together with someone else's connectivity that goes beyond that. And that could be another service provider, it could be an enterprise, it could be the end user, it could be the device internally, or even a accessory like earbuds or something like that. And I think there's a bunch of questions around AI that come here, which in terms of both causing extra problems and potentially leading to solutions. So we had reference to agentic AI, and so you may well have, for example, on a video or voice call, AI in the call path, but you also might have AI able to mitigate, skipping over drop packets or anything like that. So I'll come back to that later on. This phrase that I actually used it on the similar webinar last year, informed adaptivity. So going from a world where you've got adaptive applications to ones which are adaptive based on much more enhanced information about the user and the path that the data or flows are taking through the network. My sort of overriding concern thinking about this is that we're going from a world where there's a few corner cases that get in the way of our nice theoretical approaches to mitigating latency and also throughput and quality issues. So we've known about things like, business users with VPNs or mobile roaming for a long time, where user might not be exactly where you think they are, and the path to reach them might be more convoluted than you imagine. We've been reasonable in sort of saying that those are corner cases. But the thing I see now is that those corners are getting bigger and more diverse. And in particular, that we're starting to see a range of consumer-oriented VPNs, but also things like multi-hop with meshes in homes. There's an increasing variety of network bonding and backup and failover approaches, whether that's gluing together fixed and mobile networks or multiple mobile networks, not all of which will have the same capabilities. So you may be in a situation where you're attached to one network that supports L4S, but another that isn't. What happens? Multipath TCP, but what happens with UDP? And so there's a lot of other possible scenarios. And I see that getting only even harder as you get into things like cellular connectivity with network slicing and so-called quality on demand APIs, where you might have third parties in the mix as well. So it could be an in-building neutral host that is running their own private network, where your network is a tenant on their infrastructure. Private network to public network connectivity, that's becoming an issue, and hybrids of varying sorts. Satellite. Increasingly, you may not know if there's an intermediary leg of the connection that goes via satellite. We've had satellite backhaul for, I don't know, remote cell sites for ages. Now have satellite for fixed broadband. Increasingly, we're going to have satellite connected to mobile devices of one sort or another. And that brings in a whole new set of issues if you then have to build in not just the delay around the IP part of the network, but over the link to a low Earth orbit satellite. There's potentially even some additional entertaining factors in there from Doppler effects and a few others, because you're essentially dealing with a moving base station. And then above all, there's this role of AI, where is the end user actually a human, or is it an AI agent operating somewhere on their behalf? So you think you're speaking to Dean, but actually you're speaking to Dean's AI that might be running on my iPhone, it might be running in my home gateway, it might be running in an edge cloud, it might be in a completely different data center. And it's essentially, I've empowered that AI to have a conversation or a Zoom call on my behalf, or look for trigger words for a vulnerable person doing anti-spam and anti-scam detection, and you get a whisper in your ear saying, "Don't give that person your bank account details." Where you're going to be forking or having inline intelligence in what looks like a transaction to an end user, that geographical location and the latency associated with what you thought were known links starts to become ever trickier. So there's a fundamental issue here is do you have network coverage? And if you do, is it got sufficient capacity and capability to do what you want in terms of the latency management techniques, whether it's L4S or anything else? And the easy answer is if you're in this setting, if you're at home watching Netflix on Wi-Fi or a fixed Ethernet to a cable or fiber connection that is reasonably predictable and guaranteed, then we can apply all of the techniques we've heard about because the actual physical environment is pretty much fixed. So you take out a lot of variables, a lot of constraints. And for a large amount of the value in internet connectivity, we're in this sort of setting. Certainly the largest amount of traffic is doing what this person is watching a video, what I'm doing now, where I'm sitting in my office on a reasonably stable connection. But the problem is that's only a part of the overall world of connectivity that application developers and content providers have to think about dealing with. There's a lot of an increasing set of scenarios where the network coverage is either unreliable, unpredictable, or unmeasurable, and there's issues around control and capacity as well as coverage, and also capabilities, particularly some of the more fine-grained abilities in things like 5G or later versions of Wi-Fi. And you can categorize these into sort of four buckets, if you like. First thing is mobility, and mobility brings both the challenge of not knowing if the network is going to be connected all the time, but also the physical realities of dealing with it could be a ship on the sea in and out of cellular coverage. Maybe it's got satellite, maybe it hasn't. Aircraft. Actually, connectivity in aircraft is getting a lot better if they got satellite connections. I've been on a few flights recently with Starlink, and it's notably better than the LEO or the Earth to Air, ground to Air connectivity. In fact, I flew on a flight recently where the pre-flight safety briefing, it's the first time I'd ever heard an airline say, "Please do not use VR headsets during takeoff and landing." And to be fair, the latency was pretty good. But again, we don't necessarily know about that from the application point of view. Trains, it may well have metallized windows, you've got tunnels, you've got all sorts of issues there, and that's an important part of connectivity. Indoor and inside, I can talk about indoor for far too long, but there's a lot of challenges with indoor connectivity, whether that's an apartment block or what's called an MDU, or it's an industrial premise, such as a factory or warehouse with metal walls and lots of concrete and steel everywhere. Or it's a large area like, say, a port or an airport, which doesn't always have good connectivity from the public network, where you're perhaps relying on private connectivity, which, if you're a cloud provider, you might not know how to interact with that. Remote areas, again, we're well known. It could well be that there's a basic level of coverage, but not enough capacity to reserve bandwidth. Maybe you're not going to get the full 5G standalone if it's cellular. Maybe you've got satellite, but it's a thin connection, or potentially even seconds or minutes or tens of minutes of latency for things like some of the satellite messaging applications. And then there's this sort of virtual realm where you've got split tunnels, where you've got AI agents, where you've got VPNs with varying levels of sophistication, SD-WAN and network as a service, which might change the nature of the connectivity dynamically. So all of these are scenarios that can impact latency in the real world. I'm not going to talk through all the different types of indoor environment, but there's a lot of ways of delivering connectivity inside a public building or a private building, which may well involve a third party. And so you then think about how you manage and optimize for latency, which transits 2 or 3 different network providers and domains, which may have their own core and intelligence layers and their own commercial and regulatory objectives as well. I think this issue of boundaries is one that's going to crop up more, both on the fixed side and on the wireless side. There's increasingly going to be multiple hops, and that could be because of regulatory separation between network ownership and service providers. It could be through advances in roaming, indoor and third-party neutral host solutions are becoming more important for cellular in various locations, Wi-Fi federation, Wi-Fi offload. perhaps an AI layer that's facilitating all of this. So you've actually having an AI agent which you've given an intent to set up this type of connection for this purpose, which is great from a usability point of view, but you then perhaps have AI latency because that's mediating the connectivity setup and configuration and teardown. So there's a lot of other things to consider as we go forward. What we will find is that there will be certain environments which have well-engineered or deliberately engineered networks, which could be on private 5G network, or it could be a public venue where they've set up to do, I don't know, real-time monitoring from a camera inside an F1 car or something like that, where you absolutely will be able to do either deterministic latency or at least low latency because someone has engineered around all the problems that I just talked about. But those are going to be isolated, and whether it's scalable and universal as a developer, you need to think about whether that's the case for one specific example, and what happens for someone sitting at turn 3 with a smartphone with a local network is whether that's different to someone who's watching the same thing on a bus, 1,000 miles away. So I would say to sum up, I think we're going to need to understand user context as well as the device and other normal sort of measurable internal parameters. We need to look at the external world and external context of end users. We might find that you can use AI tools to deduce some of this. I think there's going to have to be a way of understanding for a given application and a given user class some metrics and heuristics for predictability and reliability. We need to think more about how the interoperability, where you have these multiple service providers or network owners in a chain, how you can manage latency across those boundaries, possibly with standards and collaboration, but also perhaps maybe one thing that hasn't been mentioned today is whether we can create more latency tolerance. You can probably drop a quarter of a second from what I'm saying and use an AI engine to reasonably accurately fill in and predict the gaps of the next word I am going to say. That's not always going to be the case, and there's certainly some regulatory hurdles for that. But I think one of the things to think about here is whether we have a layer of AI varnish over our user experiences in future to cover up some of the imperfections underneath. And with that, I'll turn it back over to Bjørn and see if there's any time for Q&A.
All right, thank you very much, Dean. That's very interesting stuff. I like the slide you had where it's like mostly corners. It's very good.
I just we use it once. We either use the term corner case or edge case, and it just strikes me the corners. There's more corners, and there's more edges.
Yeah, indeed. Yeah. So do you think this, like you mentioned some examples from some examples of the exceptions from this corner case premise?
Yes.
Can you go into some more detail about like what are those examples where you can actually trust that the network will deliver low latency?
Right. Well, I mean, the most firstly, I would say that in general, the fixed domain is more trustworthy than mobile because you've got fewer physical effects like radio interference and blocking and mobility and unexpected clustering of users. So I think that as a general rule, fixed line is more predictable than mobile. In mobile, you'll get patterns aggregated over a large number of people, but what you will find is there's certain locations that are well engineered. So it could be a football stadium or an F1 circuit, or somewhere like a really busy trafficked downtown area where it makes sense for the operators to really model that properly. And we'll certainly see AI tools being used for the design and engineering of networks, and also to look for anomalies and unexpected variations and think about how they can be managed in software. Whether that's within the radio with things like beamforming, or whether it's perhaps dedicating resources to VIP users or something like that. There's a lot of work going on around the network APIs. I'm not sure whether they've gone all down this path as far enough to really get to optimizing latency on a per user basis. I think that you might find that there's a couple of VIP users in a cell. Maybe you're doing broadcast uplink or something like that, and you request extra capability or a slice. but there's likely to be an inventory management problem there of how many resource slots do we have. So if you're Instagram influencer number 3 looking for an uplink, maybe you're out of luck and you're told to wait in the queue until one's free. So I think that there's going to be a user interface aspect to that of managing expectations. So I think there's there's some positives here, and I think that the more that we deploy fiber, that gets rid of some bottlenecks. So you still have the buffer bloat and IP layer issues, but from my perspective, and correct me if I'm wrong, they are being addressed, even if the solutions are not widely deployed yet. But at least that we can characterize the problems and deliver the solutions if asked. As I say, radio is got inherent unpredictability in it, which makes it harder.
Yeah, I think you're right about that. There are a few more questions, but I think we need to move to the next speaker. So if you have time to answer those in the chat, that would be awesome.
Great. Thank you.
And thanks again, Dean.
Thanks. Cheers.
All right, next is Jeremy Austin, Senior Product Manager at Aterlo. Jeremy has been active in the telco and ISP space for 25 plus years, with a current focus on generating customer experience insights from Aterlo Network's Preseam solution for regional network providers. So Jeremy, please begin.
Yeah, thank you very much, Bjørn. Is my slides good?
Yes, we see your slides.
Awesome. Thank you very much. Yeah, it's great to be back here at 4.0. It's been really fun to see this this webinar series evolve. This is my favorite recurring yearly webinar for sure. It's really unique in the industry. And yeah, thanks both Bjørn and Victoria and the whole team at CUJO. And yeah, Dean, this is a tough act to follow. We've had some really great talks here today, but it's really fun to see a variety of perspectives here. Last time I gave this particular update was at 2.0, where I talked about the customer experience overall and what sort of latency histograms we could expect in well-managed fixed wireless networks. And we now have enough fiber data that we're going to be able to do direct comparisons, kind of following on Dean's last point there. Preseam for regional ISPs, it's a unified platform to monitor, analyze, and optimize fiber and fixed wireless access networks, really any access technology, with a strong focus on tools for customer support and access network ops. What we discovered was you really need to have a full understanding of what the hardware is doing to really be able to help an operator to mitigate problems of latency. It's not just enough to do better queuing, although that is a very, very important first step. So I'm going to present an ISP-centric view of the world, view of service delivery here, rather than application-centric. In my opinion, application-centric is at least implicitly about unfairness. I want my traffic to succeed, possibly at the expense of others, and ISP-centric is, or largely ought to be, application agnostic. Not that you can't provide service differentiation, different experience to different applications. It's that you can't predict ahead of time what applications are going to need without some kind of application network interaction. And pitting one application against another is undoubtedly pitting one subscriber against another. So I love that slide as well. On corner and edge cases, the edge is the new center. You really can't predict what the center is going to be. So looking at our QoE features, a subset of our platform, we really look at acting as a middle box there, latency management per flow AQM, similar to some other people you'll hear from today, and we do marking L4S. I think it's really interesting the highly granular payload monitoring that we do with throughput, latency, and loss and retransmits. And we tie all of that back to the network topology for deep insights and combine that with PHY statistics. So I'm going to be presenting some of the analysis that we do on a yearly basis. We've been doing this since 2018, and we share that back with the industry. So fixed wireless, combining that in-home Wi-Fi with one or more additional hops of latency variable wireless in the last mile. It has the same capacity problems that are present in other technologies, but it's more acute, than it is on fiber for sure. So our reports often referred to by ISPs as they do network planning, as work with policymakers, and we really think that it's important to have a full picture of what's happening on the network when degradations occur. So very briefly, I'm not going to read this slide. This is for your reference. This is how we do latency measurement in the home. We don't do packet injection For Delta Q, for example, you do some packet injection, but we don't have to have running code on the handset or remote devices. So we can do very good visibility with the same kind of statistical analysis, measuring downstream or upstream latency as needed. It was great to see, Gavin Young in the very first presentation showing the result of comparing latency distributions. We think that's a very powerful technique, and we've done much the same for detecting access network congestion versus Wi-Fi problems in the home. Let's get to the fun charts here. This is a chart of global ISPs in our customer set. So this is ISPs that are managing latency well, using at least FQCODL, usually a combination of FQCODL and Cake. And 2 years ago, I presented this chart. We had a slope of peak busy hour download to upload. We had a slope of 10 to 1. And I predicted that that slope would continue to decrease. It has continued to decrease. Last year, it was 8 to 1. This year, it's 7 to 1. A very neat trend line here, trending toward more symmetrical services. This is peak busy hour. So I also, for interest of comparison, did all times of the day. And all times is trending at about 6.6 to 1 for fiber and 6 to 1 for wireless. So pretty close there within a margin of error. And for latency purposes, it's not really practical for wireless networks to be symmetric, but we should still expect to see demand continue to rise. I've been at least predicting 5 to 1, and it looks as if we're going to achieve that pretty soon here. So peak busy hour is this average across all subscribers, whether they're active or inactive. So this isn't a measurement of how much a user is consuming during the peak busy hour. One of the things that we try to figure out is, as plan speed rises, how much does consumption rise? And one of the really interesting things that we see looking across, a large variety of ISPs is that at the 50th percentile, in upper plan speeds, usage is essentially flat. People have enough speed, I know people don't like to use that word, but in terms of the limit that's being applied by the plan, once you're over a certain threshold, you really don't need a whole lot more capacity there. And in the 80th percentile, we do see a rise, but the slope is very gentle as you're trending upward. This particular chart, I'm showing wireless and fiber here, noting that they're really very, very similar here. From a service delivery perspective, the biggest difference between the two is going to be latency, not total consumption. When we look at the kind of the left-hand side of this chart, though, and not do a trend line, there's something still really interesting happening here. Under about 50 to 75 megabits per second, we see a very sharp fall off. I call those legacy plans. Those are plans where the plan itself is the constraint. If you're on a 25 megabit plan or a 10 megabit plan, there's parts of the world where that is very much still true today. You are going to be constrained by the plan. So it's important to remember that most users are not going to be constrained by the backhaul or the upstream peering. But if you are being constrained by the plan, your needs are really not being met as an end user. But over 100 megabits or so, it's really hard to argue that most users aren't being met the vast majority of the time. Comparing latency here, we have the 5th and 95th percentile for both fiber and wireless, and essentially wireless adds one additional hop. That is what we would expect intuitively. Most packets are terminating on Wi-Fi, and the idle latency on Wi-Fi is going to be pretty good on both technologies. You see that additional 20 to 25 milliseconds provided by, in a fixed wireless network, you have one additional hop. And here's the same data presented as a CDF, continuous distribution function. As we expect to see, there is a rise in latency in both technologies that's very similar. You can characterize that in very much the same way. So context matters when we're talking about technology versus technology or user experience versus user experience. I think it's really important to see what are the other context around that user. What plan speed are they on? How is that being delivered? Is there congestion in the network? Is the Wi-Fi poor? Congestion moves around based on time of day and other environmental factors. So when we're comparing technology, we really think it's important to actually start to differentiate by the product that's being delivered to the consumer, rather than to say all users are having the same experience. They really are not necessarily having the same experience, and the product can be an important part of that, particularly in parts of the world where people are buying slower speeds. I'm on Starlink myself. I have what I can get, and I expect that my behavior should be very similar to others who have similar plans available to them. And then when we're doing cross-vendor analysis, we really need to look at both, how the network is actually delivering that, as well as that service and payload context. So, story so far: busy hour and all times are trending towards symmetrical usage. We're seeing, downstream usage is the rate of downstream usage is definitely dropping. The rate of growth in downstream usage is dropping. We've seen that certainly in mobile networks, and the fixed networks are catching up to that. Download demand is very similar across access technologies. Tiny plans are constrained, and fixed wireless has one extra wireless hop. So you can find all of these charts and many, many more in our yearly ISP network report, if that's of interest to you. And if you have any additional questions, you can drop me an email at jeremy@preseam.com. I think we're right about 10 minutes, Bjørn. How are we doing?
Perfect. Exactly 10 minutes.
Awesome. Thank you.
Thank you very much, Jeremy. It's very interesting. And I have a question.
Yeah.
Do you have in your data any indication of like how many users are power users and like are affected by those slower plans?
Absolutely, yes. I think you can really characterize as users much as you can characterize like density of users. You can it's really a power law distribution. So there's going to be a few users who are very heavy users, and I didn't plot the 99th percentiles on the charts, but they can get kind of extreme here. they go off the edge there. But whether a heavy user is actively being constrained or not is very much going to be a function of how well that experience is being managed, rather than just purely like the burden on the network. Because there's so many users who use very little data that I don't think it's really. I'm not sure that I'm answering your question very well, but we do absolutely characterize users on the basis of what they are. How much they consume. We characterize it based on how much they are using when the network is congested as well. It's one of the metrics that we produce for operators, so that they can assess, looking at a particular piece of technology, they can say, maybe I really need to be rebalancing how I'm distributing traffic to my end users so that those heavy users can still get the traffic that they need, but are not causing an impact to other users on that same shared medium.
Got it. I think you did answer something very close to my question.
Thank you.
You answered whether you have the data, but do you have any numbers on like how many users are power users and would be like in those different bands?
That's not in the report. Yeah, that would be a
Okay.
fun one to do in terms of percentage. Well, because we would really have to do, when you do a histogram, the right hand end gets very pointy. So
Oh, yes.
in terms of like producing insights from that, that would be a fun one to do. But what I find is that's not necessarily predictive of what you need to do in your network, because the percentage of users that are really heavy users is so small.
That makes sense. It's just an interesting stat to. All right.
Yes.
And there's another
sure.
question here as well, which is how did you measure download demand as opposed to actual download load?
Yeah.
From
I'm not sure that I understand that question entirely.
I guess
that is
yeah. I guess the question is like, how do you know that there isn't additional demand that wasn't met?
Constraint.
Right?
Yeah, that is a classic problem, and of distinguishing between constraint in supply and reduction in demand. That's when you don't have a full outside view of the network end to end. You know how much the server was sending. As a middle box, there are several ways that you can detect that. One way is to see how much traffic is being dropped, for example. Another would be if the traffic is not experiencing congestion, you'll be able to tell that from the behavior of the traffic. So the fact that we also then bring in statistics about the network allow us to tell whether the network was experiencing congestion at that time. So we do a lot of analysis to determine, like, are there other causes? For example, are there upstream reasons for a reduction in supply that are not going to be visible within the ISP operator network? So yeah, that's a really good question. We do try to distinguish between those cases. Yeah.
Yeah. All right. Thank you very much.
Awesome.
And
thank you.
With that, I think we'll move to our next speaker. Our next speaker is Frantisek Borsik, also known as Frank, COO at LibreQoS. Prior to joining LibreQoS, Frank worked with Turis, on Wi-Fi routers based on OpenWRT, and was also part of an antenna revolution bringing new horn antennas to ISPs worldwide. Today, he's working on another revolution, fixing buffer bloat, latency, and jitter, and bringing open source quality of experience middle boxes to every network, not only ISPs. So Frank, welcome.
Thank you very much. Can you hear me?
I can hear you.
You can hear me?
Clear.
You can see my slides?
I can, yes.
Yeah, nice. All right. So this was the typical type of presentation that Dave Tech was having by the end of the year. Sometimes it was at Understanding Latency. Sometimes it was at Linux Plumbers or other conference. And sadly, Dave is not here with us anymore. And he was the guy that basically started this whole field of fixing latency with Jim Geddes. And I would like to continue this type of presentations that he was having, and we are here for that. So thank you very much, Dave, for doing everything, and also for bringing me personally to LibreQoS and to the world of latency. And yeah, sadly, 2025 is basically almost the same as 2024 with some notable improvements, and we would like to give them a shout out. Yeah, so sadly, most of the ISPs still have buffer bloat, and it's really sad because like all the tools that we need to actually fix this issue worldwide in like across all the technologies and fields are here, but they are not deployed. They are users at homes mostly, not in enterprise sector, that are fixing their home routers with SQM, mostly OpenWRT based routers, and this is amazing. Right, so as always, 5G is still really, really horrible, and it's not that uncommon to have 1 second and more, sometimes 4, 3, 5 seconds of latency on 5G anywhere in the world, right? And yeah, people are bragging with their speed tests on 5G, and they can show like one gigabit of download speeds, right? And but latency is still there. So buffer bloat is still an issue on 5G, and it's a huge issue. And basically, the industry was forced to build a solution, a variant of cake auto rate, just to fix the 5G inherent buffer bloat issue. So don't believe anyone that will tell you that 5G is fixed and it's all latency. It's not, and they are still there, or rather already they are trying to sell us 6G, even though it's not as finished as a standard yet. Right, Starlink is another thing that we can touch, or satellite internet in general. Starlink is connecting more than 8 million people right now, and latency on Starlink is better than latency of most of the terrestrial ISPs, which is, like, I would say, pretty sad, because the terrestrial ISPs they have like all the advantages and all the tools available to them, and there is no such complexity as with satellite internet. So they should definitely go better. Later on, when you will get access to the slides, you will find some of the measurements that you guys can use. And I just realized that for whatever reason, yeah, so this will be better. Yeah, so you will be able to see the measurements tools that are used by for example, people at the University of Victoria, and you can follow them, you can check them out. And out there also, like Starlink is publishing some of the data. They are not sharing as much as we would like to, but at least something. And obviously there is new improvements or sharing of more information from Amazon. We all knew about Project Kuiper, but they were renamed recently as Amazon Leo. And finally, some of the people from Amazon that are aware of QoE, QoS, queuing mechanisms, got back to us on Starlink bufferable mailing list. So if you are not a part of either Starlink or any other bufferable mailing list, I suggest you to join. And let's hope for Amazon to really skip over all the mistakes that Starlink did at the beginning, and let's hope that they will really implement FQCodeO or Cake or something else that might be working on, and they will have the latencies on the point right from the start. OpenWRT is doing the best in the router world in terms of fixing latency, and one of these companies that I would like to highlight today is GLINet. In my view, and as well as in Dave's view, they were having the best OpenWRT router on the market, routers rather. And one of their improvements in their latest beta is the QoS settings directly in GUI. So you don't need to go and install a new package for SQM or something like that. Is the part SQM itself is a part of the GUI, as well as the special right now and at the experimental stage of QoS settings. So right in the GUI. A really notable addition to the Cake family in 2025, in the spring of 2025, was Alta Labs. The company is run and it was started by former Ubiquiti Networks people. And so they have Cake right now as part of the routers. And we hope they will add it to the APs later on as well. This is huge. So Tarana Wireless is the first fixed wireless radio and antenna manufacturer. They actually got solution for latency right into their product, and it will be FQCodeO, which is really amazing. And let's hope that some of the other fixed wireless manufacturers will follow the suit. Obviously, it's really CPU and other resources sensitive, so it's not easy to implement these algorithms right into the hardware and software. But let's hope that somebody else will follow the suit as well. So now let's talk about QoE middle boxes. Market started circa 2017, and as of now, we still cover only 4% of the entire ISP market. Like it was little bit less than 3% in 2024. So there is some improvement. But to add some perspective, AppLogic, formerly Sandvine, right now they are serving sometimes some 200 plus clients all around the world and helping 2.5 billion users with the latency in more than 100 countries. But, you know, and still yet together combined with all the others, Bequant, Cambium Networks, Paracum Technologies, Presim, and LibreQoS, we cover less than 4% of the market, which is like a long way to go, right? We have work to do. There are improvements in other fields that will more or less have some connection to latency. XTCP2 is one of them, and Dave Seddon said that hopefully in Q1 2026 it will be released, and it will help with monitoring latency in Docker and servers for the people. This should be huge. So all of you probably know about XDP, Express Data Path, and the guy behind it, Tom Herbert, almost exactly today, after 10 years since introduction of XDP, introduced XDP2. And the goal is to let you write your data path in any language you like to use, but be able to convert it into either P4, DPDK, and anything else that you would like to actually use. So if this will really get traction, it has a lot of potential to help. So there are more slides, and you will get more information about it when you will go through the slides that will be available on the website. yeah, and right now you can find it on GitHub and get in touch with Tom Herbert if you want to. We all do speed tests, right? Speed tests, and one of the additions this year that I would like to mention is ORP, and we will hear about ORP later in the course of this event. I think it's on Wednesday, and it's like founders or at least one of the founders of ORP. They were in touch with Dave when they were developing ORP, so it's another wonderful tool. And LibreQoS, we have added the speed test this year as well. There are also another lovely things that you will learn about. Purple Cake will be presented today right after me. FQPy will be presented later this week, if I remember correctly, on Wednesday as well. There is obviously L4S, a lot of L4S in the event. And Jonathan Morton of Cake fame is also working on new QDisk as well. And if you really want to follow Jonathan's work, it's really good to be on the mailing list. So another plea to join the mailing lists. MQCake is not presented here, but it's a way or it's a work of Toki Hoyo and Jorgensen of FQ Codel and Cake in addressing the multi-core scalability of Cake Shaper. It's coming to mainline Linux soon, so we will see the improvements with Buffer Bloat and MQCake. This is another piece of Toki's work, and you still can get free 2 hard copies of Buffer Bloat and Beyond, the seminal work on this topic that everybody should read. So please go order or maybe just download the PDF of this amazing work. And here is just a shameless plug of LibreQoS. So we have added some 700 ISPs this year. That's quite something. That's basically more than 1% of the overall market of ISPs. We also won the Product of the Year at Vispapalooza this year, the premier and probably the most important ISP event in the world. We have added some features like AI. Everybody's adding AI. So in our case, it's an assistant that will help you to automate and do reporting from the data in your network, and also do translation. Like you can use any language basically, and to speak with your network. We have added API as well, and we are working on monetization. And we have introduced speed tests. In which the focus is mostly Buffer Bloat, and we were trying to address all the issues with the modern speed tests that Dave Techt raised in the years, and I suggest you to try it as well. This is thank you, but it's not all. At Vispapalooza, there was an amazing discussion between all QoE middle boxes out there, and the topic was the notion that bandwidth is a lie, and there will be more speakers, especially I would mention Jason Levingood of Copcast, that will allude to this notion that we should all understand and we should all move beyond bandwidth and do whatever we can in order to focus people on the more important metrics that are even more important in the years to come with the latency sensitive applications. And there was also slides with additional reading, and this will be available just for a click from the slides that will be shared by CUJO AI people at the website. So thank you very much, and I will be happy to take questions if there are any.
All right, thank you very much, Frank. I have a question. So the 4% market penetration for ISPs, is that counting like small and medium ISPs only, or like is it by subscriber, or is it by number of ISPs? How do you arrive at that number?
It's the number of ISPs that are using
Okay. Got it. And then I guess would you say it's a fair assumption that the remaining 96% have pretty bad buffer bloat, since they are not,
yeah,
they don't have any of these solutions?
It's crazy, right? So people still believe in throwing bandwidth on it. It's like you speak with everybody. They still believe it's about throwing bandwidth on it. Like it's painful. So we have a lot of work to do.
I think you're right. All right. Thank you very much, Frank.
Thank you very
I
much.
think there are a couple of questions in the Q&A. So if you have time to answer those, that would be very nice.
I'm on it. Thank you very much.
Okay. Our next and final speaker for today is Duncan Cameron, a doctoral candidate in the Wireless Networks Research Group at Victoria University of Wellington in New Zealand. Duncan's research focuses on wireless broadband access for remote and rural communities, wireless ISP networks, energy-aware routing, and wireless network performance measurements, with recent work on buffer bloat and how it degrades real-world performance for interactive applications. So Duncan, please take it away.
Good morning, Bjørn. Thank you very much. Sorry, bear with me, everyone, while I just get this presentation shared here. And would you be able to tell me if that's just gone full screen there?
That has, yes.
Perfect. So good morning or good evening. It's currently 6:20 a.m. here in Wellington in New Zealand. And I'm Duncan Cameron from Victoria University. This is my presentation on Purple Cake, or simply called Purple here for dynamic control of cake. So just a quick overview of the presentation structure. So we'll start off with an overview of the actual problem that we're trying to solve with Purple, which, to sort of get started though, this will cover a pretty good history of buffer bloat, sort of existing practical solutions before we finally get into introducing Purple and kind of where it's heading next. So what is actually the problem that we're trying to deal with here? Well, active queue management solutions like FQCodel and Cake work very, very well with sort of predictable set bandwidth limits. So obviously in wireless networks, this can be a problem where you have variation in bandwidth. We just have a little figure there from the Cake auto rate project sort of illustrating what this problem really is. So quite often with the likes of Cake on a wireless link, you'll set a compromised bandwidth, but any sort of fluctuation in that wireless performance above that ends up being lost. So it works fine if you have consistent link capacities, but if you have variable links, you end up setting compromises, which results in lost bandwidth. And the problem, of course, more generally is buffer bloat here. So why do we want Cake on these links in the first place? And it's to mitigate that undesirable latency under load. And of course, buffer bloat is this undesirable latency that comes from a router or some other network equipment buffering too much data. And that's the definition from the bufferbloat.net project. So sort of just building off of that. So if a router doesn't use this a bit algorithm, it simply places every single newly arriving packet at the end of a single first in, first out queue waiting to be sent by your ISP. So of course, if these packets arrive at the router faster than they can be transmitted to your internet service provider, a queue builds up. And from time to time, that queue might hold dozens or hundreds, or in some cases, potentially even thousands of packets. So this can potentially cause multiple seconds of this noticeable latency or buffer bloat. And how did we get here in the first place? So memory became cheap, and of course these buffers act as a shock absorber that allow us to deal with bursty traffic. However, these reasonably sized buffers can become oversized when the link rates and path delays fall below nominal values. And that's a quote that actually comes from one of the early pieces of work from Kathleen Nichols and Van Jacobson. And just to actually go back to one of these early diagrams which Nichols and Van Jacobson provided, so they give the rate mismatch in a cable modem example where you basically have this client premises router equipment here on the left and then the cable modem on the right-hand side. So between that router and that cable modem, you've got some sort of predictable link capacity, but upstream from that cable modem, it could be variable 2 megabits a second up to some unknown amount. And the quote that they so well use there is that the modem's buffers are the faster slow transition, and that's where the queues build up. So inside a sealed box outside of our user control. And of course, any differentiated services queuing and buffer management at the router is very easily defeated just by having a full queue in this cable modem here. And if we think about what this actually looks like in a wireless context, we actually have exactly the same scenario. We just swap out that cable modem for a wireless link. So suddenly we have this link capacity going up to the radios, and then from there it might vary from tens of megabits a second to hundreds, but throughout the day, especially given that we're transmitting into shared access media, it can vary drastically. So yeah, we end up with that same situation. And just to sort of put figures to this, so in practice, this might look like a site router, a wireless site such as this, which is one that our research group used to run in the rural Horowhenua region of New Zealand. And you've got a router, predictable link capacity up to radio, and then that wireless link with some unknown amount of capacity that changes. So how do we actually show this sort of overqueuing and buffer bloat from actually happening? So if we look at some of these plots that we've taken from data in these wireless experiments we run, so we can pretty easily load up a link with no active queue management on it, just using something like iPerf, and we'll very quickly see that there's a noticeable increase in round trip time just in the red here. So whenever this round trip time increases above 5.5 milliseconds, we see it plotted in the red. So that's definitely undesirable latency under load, but do we know it's necessarily buffer bloat? And if we just think back to this example again, so this shake cake egress bandwidth for this router here, you pretty much got that known link rate, which on this case might be, say, 140 megabits a second. So just keep this in mind, and we'll skip forward to sort of how we can actually emulate this to know when this is undesirable latency under load or buffer bloat from actually happening. So in this little figure here, so there's a fair bit going on, but we can actually show the sort of normal rate match case, which is desirable. So this is using the Common Open Research Emulator, and we're sort of recreating that basic topology. So up on the top left there, we have node 3. So that's a router that's connected to an emulated wireless link, and that emulated wireless link has a capacity, in this case, of 100 megabits a second. And we can see that the cake bandwidth set on that link is 100 megabits a second also. So we see latency under load in this case is very good. So the packet backlog sits at under 5 packets under load. So that's normal. That's nothing we need to be worried about. But if we actually think about a rate mismatch case, we can change this bandwidth, the mismatch. So on the router there, it's actually set to 110 megabits a second, whereas the known wireless capacity on that link is only 100 still. So we're trying to feed 10 megabits a second into it more than what it can actually support. And suddenly, with a maximum queue length of 100, that actually puts us up to the backlog, sort of averaging around 90 packets under load, which is, in this case, we can see it's quite clearly a standing queue and is definitely buffer bloat. So queue that does not go away in one round trip time is bad queue, and good queue is the minimum queue size over a sliding window. And that's a quote from Jesper, and from his presentation, Beyond the Existences of Buffer Bloat. So in our actual wireless testbed example, we went back at some of our data and analyzed it. Actually, from that wireless site, there was a little photo of. And we saw that throughout the day, busy hour, quite often, even though we have cake set up on this link. There is variation, of course, just given that this is unlicensed backhaul, and throughout many times of the day, we're doing that with standard queue, and this undesirable buffer bloat from is actually occurring. So some of the results showed this bottleneck queue working as expected. The buffers are acting as a shock absorber, but we also have to consider the intended behavior of flow queuing and queue management behind this bottleneck. And we do see overqueuing, even if it's sometimes only a few milliseconds from the queues being poorly managed, just because of that rate mismatch. And what does this actually look like in practice, though? Well, let's get into it. So going back to that same wireless site, we see that sometimes we look at this top line here. This is actually the radio's self-reported capacity. There's a huge amount of fluctuation in it. And if we, at some point, actually load the network up, we'll see in the next figure what actually happens here. And we get these massive spikes in latency, which is sort of exactly as you'd expect. You're getting near the maximum utilization of the radio. More data is actually stored in those buffers, and we are getting that undesirable latency under load. However, you don't always capture these effects that well just from looking at long-term averages. And of course, bloat happens. yeah, so that queuing delay increases and we get the effects we've been talking about. And just to sort of, I guess, answer one of the elephant in the room questions about this is, well, why can't you just track whatever the radio says its capacity is and set that as the cake bandwidth? Well, some manufacturers are a lot better than others at this, and also just given that Wi-Fi where these vectors are being used without license, it can fluctuate heaps. And in this case, in the bottom subplot here, we actually see that sometimes the radio's self-reported capacity actually drops below the achieved throughput over it. So they can't be taken at face value. In that case, even the moving average occasionally does drop below it. So what do we trust? We have to have some sort of sanity checks on this data to really be able to use it. And there have been practical solutions for this problem, and the cake order rate project is probably the best known one of these. It deserves some love if you want to check it out on GitHub. There's a link there to it from where this figure's from as well. So it monitors this receive and transmit utilization and the ping response time from reflectors, and it just cakes download and upload bandwidth rate and controls latency under load that way. So a lot of people were using this for Starlink and believe still are, and it's equally applicable for other fixed wireless access products as well. And of course, our solution to this, what this presentation is actually about, purple. So red and blue Q disks, obviously some age now, but red and blue together create purple, hence the namesake for purple cake. And sort of idea behind purple was the estimated useful capacity on these fixed wireless links, and then controlling the bloat through dynamic adjustment of cake's bandwidth parameter. And we sort of extend this to actually use precise one-way delay where we have, well, GPS synced clocks to be actually able to do unidirectional measurements of the latency. And purple AIMD, there's two variants of it. There's regular purple and purple AIMD, which was sort of just a proof of concept using the AIMD, which is of course made famous by TCP, which effectively we just measure the latency, categorize it as being either okay, increment a counter if it is good, and then slowly additively increase the bandwidth, which cake has if it is good. If it's undesirable, we multiplicatively cut that, and we can do that in several ways. If it's really, really bad latency, we can cut just a mild reduction. We don't go quite as extreme as TCP. We do it more gradually, just so it doesn't collapse throughput too much. And the reason there's two variants is actually because the non-AIMD version tries to use low-level Q metrics from the radios where they are available, which is actually why it got the name purple from red and blue in the first place, because we wanted to make a passive version of effectively what cake order rate was, and we did have some success with that, which we'll get into next. So to actually evaluate this, we built a little wireless testbed. So not all of these radios were used, and we actually ended up using the Ubiquiti Loco 5ACs, which aren't in the right subfigures there. So purple controls the cake egress bandwidth directly behind the bottleneck link. It's sort of the same way to what cake order rate would. And we do this because we assume we can't change the actual bottleneck or radio Q disk. So just moving on from that. So performance results from this. So by dynamic adjustment using a target latency set with purple AIMD, we're able to get extremely good control over, overloaded latency when we load up this link with iPerf or something else. It's quite good. So there's a significant improvement over the static configurations. And we found that if you don't set anything, or if you set overly optimistic sort of cake bandwidth parameters, you end up pretty much no better off than just not setting it at all. So it is very, very important with wireless links to kind of get it right. And of course, getting it right when there's so much variation can be a very challenging thing. So purple AIMD works very well. Regular purple, which is too much to talk about just in this presentation alone, but is on GitHub as well, and the proof of concept of it is, tracks the known sort of capacity of the radio, less some safety margin to compensate for, well, the fact's not always very accurate, and then actually looks at the bottleneck radio's Q metrics to see if there's backlog in that, which of course is still a lagging indicator, given that the backlog forms in software after the underlying hardware ring buffer will actually be filled on the radio. And of course, if we actually plot what this sort of useful transmit capacity we've found from purple AIMD looks like, we get this kind of TCP-esque sawtooth, which is to be expected. So There is, of course, a trade-off between the latency target you set and how much bandwidth you get, because if you set a target that's way, way too low, I mean, we're still using Wi-Fi as underlying technology we're sending on here, so there's always going to be some sort of contention, headline blocking effects from things like the clear channel assessments, which go on. And sort of just building off of that there, we can see it here as well. So the sort of just vanilla out of the box FQ codel configuration on that wireless test gave us the best throughput. Purple AIMD gave us the best latency overall, but at the expense of having the worst throughput. And that is just because we set a pretty low latency target that we wanted. We would like to sort of use regular purple in more cases, but you just can't get the low-level Q metrics in the way that you need from every hardware vendor. And of course, to actually enhance it, this is kind of where it leaves us. So need more open source support. We'd love to be able to get low-level Q metrics out of the radios, and we could pretty much come up with an almost passive solution to controlling cake bandwidth parameter, which would be awesome. And of course, yeah, and loving memory of Dave Tart. So I was privileged enough to have Dave give me some early thoughts on this work, but unfortunately never got to share kind of results of which with him before his passing. He's been a massive figure, obviously promoting the Bloat project forward in ways that most people would never have been able to do, and he's going to be sorely, sorely missed for generations. And thank you to Dave for being a massive inspiration to me and my research. And thank you for listening. If you have any interest about this, please check out our Wireless Networks Research Group website or check out Purple on GitHub. I should note though, it's very much proof of concept, and if you want something production ready, you should stick to using cake auto rate. Thank you very much.
All right, thank you very much, Duncan. Let me check the Q&A here. Okay, Adam Thompson is asking, I have many devices at layer 2 between my edge and my customer, translating from 200 gigs down to 1 gig. Each has a buffer to have bursts. I assume it's like to handle bursts. Should I be setting all those queue lengths to 0 to help eliminate buffer bloat, or is that too drastic?
I think that would be too drastic. Queues, of course, do serve a purpose. They do act as shock absorbers. They only become problematic when they're poorly managed, but that's quite a transition down though. 200 gig down to 1 gig.
Yeah.
Wow.
I guess it depends how things are split up, right? Must be. And I have a question as well about the setup that you showed. You had a table with like the impact of the purple cake, and then the other Q disks had like 35-ish like as peak latency, and the purple one got to like 16, 17. That doesn't sound like very high numbers. So maybe I misunderstood what the setup is. Is that like a local lab setup or just one hop or something?
Yeah, it's just that one's just one hop, so it's not too bad. Yeah, I guess the more important thing being, of course, if it's actually a much wider path, like several hops deep, and like say a WISP network or something, that would obviously cumulatively ends up being quite a number. So the sort of target was to try to keep it around somewhere around 5 milliseconds per link, ideally. Certainly in some markets like New Zealand, where the government's funded some of this rural broadband infrastructure, there actually is mandatory reporting on latency over links. So in some markets, very strong incentive to keep it that sort of level. But of course, it doesn't. For some people, it won't matter so much. I think there's a comment from Jeremy, sort of adjacent to that, about the rate reduction. And yeah, I do agree. So 125 to 105 megabits a second does seem like an aggressive reduction. It can definitely be tuned. So pretty much all those parameters. So I think that 105 megabit was the regular purple variant from memory. So by default, I believe I was tracking 20% less whatever the radio reports its maximum transmit capacity is. And it's you can adjust that depending on sort of your intuition for the link. So Ubiquiti tends to have very, very accurate capacity estimations from what I've seen compared to some other vendors. And sort of the same. So Purple AMD is obviously an even bigger compromise, just depending on sort of what your target is. So if you have a target of 10 milliseconds latency, it will just constantly adjust it back to that, and you end up losing less bandwidth, but obviously expensive, high latency.
Right. Makes sense. Thank you very much, Duncan.
Thank you.
And with that, today's sessions are finished. I want to thank again all of today's speakers and everyone who's attended, everyone who's asked questions. Thank you very much. If you enjoyed today's sessions, please join again tomorrow and on Wednesday, and tell your friends and colleagues to join as well. So see you again tomorrow, and have a great rest of your day. Thank you very much.